Hello. This video is going to use a simple fixed point data path to illustrate some common problems that you may encounter when attempting to implement this in Verilog using the Vivado tool suite. This data path finds a maximum of 3 signed 16-bit numbers. Signed means 2's complement encoding. The 3 16-bit inputs are A, B, and C. The thick lines in this diagram indicate buses. The thin lines indicate single-bit signals. The output Y is set to the maximum of A, B, and C. Signed comparators and muxes are the building blocks used in this data path. The first signed comparator compares A against B. The output is a single-bit signal U1_LT that is a true, that is a logic 1, if A is less than B. The signal U1_LT is used in the first mux to steer the maximum of A and B to the mux output. If U1_LT is true, that is, if A is less than B, then the B bus is steered through the 1 input, through the true input, to the mux output. If U1_LT is false, that is, if A is greater than or equal to B, then the A bus is steered through the false input, the 0 input, to the mux output. The output of the first mux is a signal called max_AB. A second signed comparator is used to compare max AB against C. The output of the second comparator, U2_LT, is used in a similar manner as it was with this mux to steer the maximum of max_AB and C to the output Y. Before we begin writing our Verilog, let's review signed and unsigned integer operations. Our data path is going to handle signed integers. Signed means 2's complement encoding. Let's do a quick review of 2's complement encoding. If the most significant bit of the number, and this is an 8-bit number, is a 1, the number is negative. If the most significant bit of the number is a 0, then the number is positive. So recall that a FF is 255 unsigned, but as a 2's complement number, it's -1. 7F, this is a positive number, it's 127 unsigned and a positive 127 as a signed integer. An 80 is the smallest negative number in 8 bits. It's 128 unsigned, -128 is a signed integer. You can go back and review the notes on 2's complement in order to get a better understanding of this. So we're going to use the Verilog comparison operator, the less than, to generate a comparator. So here we have a signal called L2 is equal to A less than B. These can be these are buses, but the output's going to be a single bit signal, and this will be true if A is less than B. Here I've declared these two values to be unsigned using the keyword unsigned. This is going to generate what is known as an unsigned comparator. Here I've changed the wires to signed types, but I've left this exactly the same way. This is actually going to generate different hardware. It's going to generate a signed comparator. So what's the difference for the hardware between that generated for an unsigned comparator versus a signed comparator? So here's an unsigned comparator. The hardware for that is very simple. It's just going to be a subtractor. We know that C out is equal to 0 for A minus B when A is less than B. So we'll simply take the carry out of the subtractor, invert it, and that becomes our less than signal. For a signed comparator, we'll still do a subtraction operation, but the logic for the less than signal is more complicated. It will be based on the signs of both the input operands and the result. So A of n-1 is the sign of A, this is the sign of B, and this is the sign of Y. We'll also call this Y of S or A of S or B of S as the sign bits. The negative flag is the sign of the output value Y, and we'll call it YS. So we're also going to have a thing called the signed overflow flag. The signed overflow flag indicates that we did not get the correct result. We had overflow. So the less than operand is this Boolean, the less than output is this Boolean equation. And we can read it as follows. If the overflow flag is 0, that means we got the correct result. Then when A is less than B, if we say A minus B and we subtract these two numbers, we should get a negative number if A is less than B. So the negative flag will be set and we'll get the correct result. However, when we do the subtraction, if A is indeed less than B, and we do A minus B, but we get a positive number instead, that is NF is a 0, then that must mean that the overflow flag is set. We got the incorrect result. So that's this term here. So the less than output is going to be the negative flag ending with not overflow flag, or the not negative flag ending with the overflow flag. So we also have to do some work in generating the overflow flag. The overflow flag Boolean equation is here. It's based on the signs of the input and the sign of the output. Remember that we typically define overflow as if you add two positive numbers you get a negative number, that's overflow, or if you add two negative numbers and you get a positive number, that is also overflow. So here we have to rethink it in terms of subtraction. So if we have a positive number and we subtract a negative number, that's like adding two positive numbers, then we should get a positive number. However, we get a negative number, the sign bit is a 1, then that's overflow. This is a negative number subtracting a positive number. That's like adding two negative numbers. If we get a positive result, that's wrong. We should have gotten a negative result. So this is also overflow. So all of this Boolean logic here plus a subtractor is going to be generated whenever we simply do this less than operation in Verilog and synthesize the design. The synthesis tool is going to translate either one of these two statements, signed or unsigned, into this hardware. So one simple Verilog statement can actually generate a lot of gates. Here's my first attempt at a Verilog solution for this max data path. I have three 16-bit inputs and one 16-bit output. Notice that I declared the inputs and outputs as signed because this data represents 2's complement integers. I have used 4 assignment statements, one for each block of logic in the data path. I have 2 comparators and 2 muxes. I've also declared some internal wires for connecting these blocks together. I have placed this file into a Vivado project, and now I'm ready to begin synthesis and simulation. The first thing that I notice is that Vivado is warning me about syntax errors. Vivado is always dynamically checking for syntax errors anytime that you enter a new statement. You do not have to run a syntax checker. I have placed this Verilog file into a project, and now I'm ready to begin synthesis and simulation. The first thing I notice is that Vivado is warning me about syntax errors. Vivado runs the syntax checker when you save the file. To see what the syntax errors are, I'm going to click on this message that says 2 critical warnings. And it shows me a couple of warnings here, and it says in my source I have a syntax error near the assigned statement at line 35. So let's take a look at line 35. Line 35 is a mux. It says for this condition right here, if it's true, pass this input to this output, else if it's false, pass this input. This statement looks correct to me. The syntax error is near the assignment statement, so let's look around it. This in module statement matches up with this module, that looks fine. If I take a look at this assignment statement right here, I notice that, oh, wait a minute, this guy is missing a semicolon. So I'm going to go ahead and put a semicolon there. The asterisk here shows me that this file is modified. I will use Control S to save the file off. At this point, it's going to rerun the syntax checker, and now my syntax errors have disappeared. Now that the file is free of syntax errors, you may think it is time to simulate. However, I am going to ask you to always run synthesis before you try your first simulation to ensure the file is free of synthesis errors. This way you will not waste your time simulating a design that has synthesis errors. Synthesis is the process that translates Verilog into a netlist of gates. Implementation is the process of mapping that netlist of gates onto the field programmable gate array. To run synthesis, I will press Run Synthesis, say OK, and look at the design runs, and this process, the synthesis process will be running. You can follow the progress of this by watching the log. At this point, synthesis is finished. Instead of trying to run the implementation, I'm going to first view reports in order to check for synthesis errors. So I have two reports that I can view. One is a synthesis report that will report any synthesis errors. The other one is a utilization report that will show what logic resources I'm using. So I'm going to go ahead and left-click on synthesis report and say Open Synthesis Vivado Report, and then my synthesis report will be displayed. So when looking through the synthesis report, you're looking for unusual warnings, and it will take a while for you to get used to what is an unusual warning versus what is a usual warning. So I'm going to take a look at this, and I have a warning here. The very first warning here on line 19 says net Y in module entity max 3 does not have a driver. Does not have driver. That's not good. A driver is logic that's going to drive a signal, and it's saying that my Y output does not have a driver. So let's go back here and take a look. This is my Y output, and it says that no logic is driving Y. Well, if I go back and look at my schematic, which is here, what should be driving Y is the output of this mux. So let's go and take a look at my Verilog and see what I have. Here's the mux right here. And oh, I see the problem. Instead of naming the signal Y here, I called it the name max, which doesn't exist anywhere in here. If I use a name like this that does not exist, Verilog is going to assume that this is a 1-bit wide signal and just generate an implicit wire statement for it. So that's a mistake right there. So I'm going to go ahead and change that from max to Y, and then go ahead and save this off. I might as well go ahead and rerun the synthesis because any other warnings could definitely be generated from that one warning right there. So let's go ahead and let's see how many warnings disappear when I rerun synthesis. So I've rerun synthesis and reopened the new synthesis report, and now I'm going to start looking for warnings. I don't see any warnings. I see some infos, and it's finished the elaboration. It's going through synthesis, doing optimization, and it's finished. Then another stage of optimization starts talking about what kind of things are inside here. It's detected a couple of muxes, and keep looking down here. And finally it's finished. It's reporting what kind of gates it's using. It's using some 2 input LUTs, some 4 input LUTs, some 5 input LUTs, input output buffers. Everything looks good, so synthesis is finished. So before we run the simulation, let's first take a look at the test bench. You will need to understand the test benches at least at some level that I give you, because you can in order to debug the design, you must understand at some basic level what the test bench is doing. So the test benches that I give you for the early projects are going to be very straightforward. They're going to instantiate the unit under test, in this case the max3 component. Then it's going to open a file of vectors that will contain values to apply to the inputs as well as the expected output. It will read each line from a file in a loop. It will apply these vectors to the inputs. It will then check the result against the output against the expected result, and if they're equal, it'll display pass. If it's not equal, it'll display fail, and it will increment an error count. Let's take a look at the vector file. So this guy right here. So I'm going to say File. I'm going to say Open File. I'm going to look in here. Here's going to be my vectors.txt. It'll always be a text file. Let's bring it up. So my vector files are pretty simple. There's each line contains a test vector. This is a comment right here. I'm not even reading that. I'm just reading the first 3 values, and I want to find the maximum of these 3 integers. The 4th value here is going to be the expected value. So the maximum of these 3 integers are going to be this 10,100. The next line, the maximum is going to be this number right here, the second number, so that's the expected result, and so forth. So at this point, let's simulate the design. So I'm going to left click on Run Simulation. I have three choices: Run Behavioral Simulation, Run Post-Synthesis Functional Simulation, or Run Post-Synthesis Timing Simulation. When you're debugging, you always want to run the behavioral simulation. That way you will be able to correlate what you see in the simulator with the RTL statements in your Verilog. Simulating these, running these simulations here are running the simulation in a net list of gates, and it's going to be hard to correlate the signals that you see in the simulator to the signals that are declared in your Verilog RTL. So always debug using the behavioral simulation. So I'm going to left click on this. It'll compile the code and start up the simulator. When the simulator pops up, as this is the first time you've run the simulation, what it's going to do is going to take all the signals in the test bench, which is here, and add them to the waveform window. So that means it's going to be the inputs and outputs of the unit under test plus all the internal signals of the test bench. This is not terribly useful. What you really want to look at is the signals inside your design. So if I click on UUT, it's going to show me the signals in my unit under test, which is in my match 3 design. So one of the first things that I always do is I'm going to delete all of these signals in the waveform window by left clicking, holding down the shift key, left clicking here, and then hitting the delete key. That will delete those signals. I then want to add all of these signals to the waveform window. So I'm going to do a left click here, hold down the shift key, and then do a right click on the last signal and say add to wave window, and it will add all of these signals to the window. It looks like I have a signal left over from the test bench, the error signal. I'm going to go ahead and delete that. So now these signals here in my waveform window reflect the signals in my design. I can move these around by just dragging them around like this if I wish. The simulator, when it starts up, also runs for 1 microsecond. So I'm going to go back, and that's actually long enough to apply some of my vectors. So I'm going to go back up here and look, and I see a whole bunch of fail messages. So that means that there's something wrong in my design. So now I'm going to actually have to debug my design, and you're going to be doing a lot of this. So in order to debug this, I first want to get my window in a little bit more readable state. I'm going to shrink that a lot. Because I want to maximize the amount of room that I have for my waveforms. I'm going to take this guy here, shrink it, put it over there, do this guy there. And now I'm going to start looking at my actual signals. Now, what I'm seeing is that, first of all, I don't have any signals, any waveforms displayed here. And that's because I added these signals after the simulation was run, so it didn't record any data for these waveforms. So I'm going to need to fix that. So let's do that. So I need to restart the simulator. So here in the TCL console in the command line, I'm going to go ahead and type restart. So let's just type restart. It's restart everything. Now I'm going to go ahead and rerun for my 1 microsecond. So I'm going to run for my 1 microsecond. Now I get some waveform information displayed. So there's 2 problems with this display. One is zoomed in way too far. I'm looking at things at 1 picosecond intervals. That's way too fine a granularity. The other trouble is that I'm looking at things in binary. So let's fix the binary first. I typically want to either look at things in hex or decimal. So if I select this signal here and do right click, and then look at radix, I can change that to either be hexadecimal, unsigned decimal, or signed decimal. So in this case, we're dealing with signed decimal numbers, so I'm going to change that to signed decimal. And in fact, I'm going to do that for all my other signals as well. So at this point, all my integers are in signed decimal. So let's now also go ahead and zoom out. So I'm going to zoom out. So let's zoom out. I'm going to keep zooming out until I see some vectors. So now let me go to the beginning where I can start debugging. So I'm going to start looking at the vectors, and you might as well just try to figure out what's wrong with the very first failure, which happens to be the first vector. So let's take a look at what this is telling us. What do these numbers mean? If I go back and look in the test bench, what is being printed out here? It's saying display %d. That's going to be my count. So that's just a line number of the vector. So at vector number 1, the next thing is %t. What is that? That's the current time. That's this guy right here. That's actually being reported in picoseconds. So this is actually going to be at 150 nanoseconds. And then the remaining is pretty clear. That's A, B, C, and Y. Where here, and it's the failed. So this is the guy here. So the actual value that it got was 1, but it expected a value of 2973. So well, let's go back and go back to the waveform window and see what we got. So we got the wrong Y value. We got a Y value of 1 when we should have gotten the maximum value is 2973. So let's just step through the design and see what's going on. So first of all, we're debugging hardware, not software. And in software, the way you debug it is you put a breakpoint at a line number and you break when you get there in the source code, or else you single step through the source code and watch what values are being changed each time you step over a line of source code. You do not debug hardware that way. Here, there's no such thing as single stepping through the Verilog. Instead, what you're going to do is you're going to observe what happens on the inputs and the internal signals at each time period. So here at 100 nanoseconds, what happened is, and let's go back to the test bench to see why this first test vector got applied at 100 nanoseconds. So let's go back to the test bench. We have this $100 says that's a pause. It says wait for 100 nanoseconds and then begin reading the file and applying the test vector. So that's why we have these values beginning to change at 100 nanoseconds here. This tick mark right here represents 150 nanoseconds, which we apply the next test vector. And why is it at 150? If we go back to the test bench, we'll see the vectors are applied, and then we pause again for 50 nanoseconds here before we start this. So that's why, and then we hit the end of the loop and go back up. So that's why these next vectors are being applied at 150, and that's why this time in this message is 150 nanoseconds. So why are we getting this failure? Well, let's go back and look at the hardware, and you have to understand what the hardware is doing in order to debug this. So what's happening is we're having A and B come in, we're going through the signed comparator, and it's choosing the maximum of A and B, which should appear on this max AB signal. So this max AB signal should get the maximum of A and B. Let's see if that happened. So I'm going to go back to the simulation. I'm going to say, okay, here's A and B. Where's max AB? Oh, it's right here, and it's a 1. It should be the maximum of these two. The maximum of these two happens to be the minus 1421, but it's only a it's only a 1. In fact, in looking at this signal, there's something strange about this signal. I see that these are buses and that they have bus, and this is a 16-bit signal, 16-bit signal, 16-bit signal, and so forth. And if I go back and look at my hardware, this should also be a 16-bit signal. But looking in here, this is only showing up as a single-bit signal. It's not showing up as a 16-bit signal. So there's something going on there. We'll have to go back and look at our design to see what's happening with this max AB signal. So let's take a look at our sources. So here's our sources. I'm going to go ahead and open up my design and take a look at this. And we're looking at max AB. So let's take a look at max AB. We said it wasn't a bus. Oh, and I see the problem. We assigned this as a single bit wire. We did not assign this as a 16-bit bus. So as a matter of fact, that's doing exactly what we told it to do. We told it this is only going to be a 1-bit wide signal, and so it only made this a 1-bit wide signal. So that's why we're not seeing the entire value that we're supposed to be seeing. So I need to correct this error. I'm going to go ahead and shut down the synthesis tool, and I'll go ahead and save the waveform configuration since I have edited it, and I will go ahead and fix this in my synthesis source. So let's go there. So here's my synthesis source. I'm going to go ahead and now make this a 15 wide bus. I'll resynthesize and restart up the simulator. So I've started up the simulation and I changed max AB to be decimal formatted number. And I'm going to take a look at this and I see that, oh, now this max AB is the maximum of negative 1421 and negative 16588. So max AB is now the correct value. Before I go any further, what I want to do is I want to go to my cursor. And I want to move this cursor back to where I'm actually observing signal values. So let's do that, because the cursor, wherever the cursor is, that's going to be showing me the value of the signals in the left hand pane. So let's go ahead and bring this cursor back over here, and so now it shows me the current time where the cursor is 1:35, and the values of these signals here reflect the value under the cursor. So that's correct. In fact, let's go ahead and see if our vectors are passing. So I'm going to go back and look in my log window. That's old messages. Let's go back to my newer messages. So let's go back to these initial messages here, and yes, it's sure enough, I get a pass on my first vector, a pass on my second vector. In fact, I get lots of passes. Oh, but I still have a failure, and the failure is happening at 400 nanoseconds. So let's go ahead and see what's happening at 400 nanoseconds and see why I'm getting a failure there. So here's 400 nanoseconds right here. Let's go ahead and move my cursor over there. And it must be the failure is going to be in these vectors right here, right before the 400 nanoseconds, because 400 nanoseconds is when I'm reporting the failure. So it's going to be this set of this vector right here that's causing the failure. So this vector is failing. So to verify that, the fail has A is 15,148, 15,148, B is negative 31,801, and so forth. So that's the failing vector. So let's first of all see if max AB is correct. Max AB should be the maximum of these two values. And it is. The maximum of A and B is negative 15,148, so it is. So now we're going to compare max. If we go back to our hardware, and let's take a quick look back at our hardware. We're going to be comparing max AB against C, and we want the maximum of this to go to Y. So let's see what's happening in our simulation there. So here's max AB compared against C. So negative 15,148 is greater than negative 23,979, and yet Y is getting the value negative 23,979. So what is going on there? It's choosing the incorrect value. Let's take a look at our U2 less than. U2, if I go back to our hardware, so let's check our hardware. Our hardware says that if U2 underscore LT is true, then we're going to be max AB is going to be less than C. So let's see what we got there. Max AB is less than C. We would have this value being true. So let's take a look at that. So max AB is not less than C. So we have a problem there. It's saying that max AB is less. So we need to go look at that statement in our source code. So let's go back to our source code and let's take a look at that statement, that comparison. And we should be comparing. It says here, the statement says C is less than max AB. Let's go take a look at our hardware again. Here, we wanted to write max AB is less than C, but instead in our Verilog, what we did is we did C is less than max AB. So we reversed these two operands. So we need to correct this error, which we'll do, and then we need to shut down the simulator and rerun the synthesis tool again. So I'll do that. So I've corrected the problem, rerun the simulation. I swapped this to be max underscore AB is less than C, just like in my hardware, max underscore AB is less than C. I've rerun the simulation, so let's check the waveform, and let's check our output. And I'm seeing some failures here. What is going on? So here, even my first vector is failing. So let's see what's happening. So I'm going to take a look at this. Max AB is correct. So now I'm comparing negative 1421 against this positive 29773, and the maximum of that should be 29773, and yet the maximum is not getting passed through here. In fact, the negative is. So what is going on here? Let's go back and take a look at our Verilog and see if we can figure out what's going on. This looks correct. Max AB is less than C. If this is true, then I want to pass, that is that max AB is less than C, then C is the maximum. That's the true value. So that's going to be the one value that maps to my mux. So that all looks correct. So something else subtle is going on here. It might help to look at this data in a different format. Let's take a look. Let's go back here to our test bench, and let's take a look. Let's put this in just unsigned or just hex value. So I'm going to do, that's going to be hex there, and I'm going to go ahead and view this as a hex number as well. And it's comparing these two hex numbers, and the output that is putting through is, let's go ahead and put Y here. Let's go ahead and change Y to a hex number as well. So it's taking, it's almost comparing these two numbers as unsigned numbers. It's taking the larger hex value, unsigned, the larger unsigned value, which is FA73, and it's passing that through. So it looks to have something to do with signed versus unsigned comparisons. Let's go back and take a look at our source code. It's almost treating this as an unsigned comparison instead of a signed comparison. Oh, wait a minute. When we modified this Verilog to make this max underscore AB to make this a bus, we forgot to put the signed here. So this is actually an unsigned number. And I'm actually mixing unsigned operand with the signed operand. When you do that, Verilog is just going to say, I give up, I don't know what you're doing. It's going to treat everything as unsigned. So I'm going to need to actually declare this guy here to be signed, stop the simulation, and rerun it again. So this is a subtle error, and to sign this can be a difficult error to find. So I'm back in the simulation. Now if I look at this, I was expecting Y to be, the very first vector is failed, I'm expecting this to be the positive number 29773, and it works. In fact, let's go and take a look at my vectors. Wow, I see a whole bunch of passes here. So I'm going to go ahead and run it for longer. So let's go ahead and run for 10 microseconds, and I get all vectors passed. So at this point, my behavioral simulation is passing. At this point, you might also think that you're finished, but you're not finished whenever your behavioral simulation is passing. I'll go ahead and close this down. We always are going to want to map our hardware to the FPGA. So the only thing that we've done so far is synthesis. We haven't actually run the implementation yet. So I'm going to go ahead and run the implementation and map this to the FPGA. Once that is finished, then I'm going to run a post place and route simulation. You're only done when your simulation passes the post place and route timing simulation. That verifies that your design should work on the real hardware. So we're done. So we're going to cancel this, and at this point we're going to go ahead and run our simulation again, except this time we're going to run post implementation timing simulation. So let's run that. So our simulation is up. If I take a look at the signals here in our UUT, one thing that you'll notice is wow, there's a bunch of these weird devices here. That's because we're now simulating the actual devices on the FPGA, and it's not going to correspond to the signals that we used to see in our behavioral model. So that's why it's difficult to debug at this level. Let's go ahead and see if we've passed. We've passed our initial 1 microsecond, so I'll go ahead and run for 10 microseconds. All vectors pass, so congratulations. This design is now finished. You have passed the post place and route timing simulation. And they need to spell passed, I need to spell passed correctly.